So I'm going to be presenting on Mineshaft thermal energy storage feasibility studies, case study at Monktonhall, Scotland. And I'm presenting on behalf of the STEAM project team, okay, which is a consortium between, primarily in terms of academic sense, University of Strathclyde and University of Edinburgh. And we had a range of industry and governance partners as well, which will be in a later slide. Just to highlight, because we've got a nice image here from Huachan Wang going down into said shaft. This is Monktonhall number 2 shaft. And one of the reasons for looking at this site is essentially what we can see there is the ease of accessibility. Another thing to point out in this picture as well is that you can see a rising main or pipe kind of line going down into the shaft. That's a legacy of infrastructure that's put in place for this to become a mine water treatment site. So that was installed by what was then the Coal Authority. Okay, so that's something to consider when looking at this site as well. Okay, so the STEAM project, so the full title, Gigawatt Hour Subsurface Thermal Energy Storage into Your Structures and Legacy Mine Shafts, funded by EPSRC, led by Zoe Shipton, University of Strathclyde. Another bunch of wonderful cast of characters here as well, work package leads and co-investigators in bold. We won't get to do detail about all the names there. Some of these names will come back up as we go through, as I'm pointing out papers, etc. But something to point out that Ian Molnar is in attendance today. So if there's anything that we can't quite fit in this talk, then I'm sure you'll be happy to talk about it over coffee. And just some other partners are listed down the bottom. So industry partners and also as well council partners as well. And just to highlight in the background here, we have the iconic Barony A-frame. So this is a site near Cumnock, and this was one of our case study locations. So it makes for a cracking photograph. So context, and building on some of the stuff that Alistair was talking about, is that thermal energy storage in general must be co-located with demand. This has probably been referenced several times already during this symposium, but abandoned mines lie beneath about 25% of all UK building stock. From the MRA mine entries database, there's over 175,000 mine entries, and the total number of shafts within that is about 78% of all entries. Okay, so in terms of initial estimates, depending on the size of your shafts, etc., if you have millions of litres in a shaft, you can store over 1 gigawatt of heat. Okay, and if looking at the overall database, if 1% of mine entries are suitable for heat storage, that could supply about 10% or supply heat to 10% of UK homes, about 2.8 million people during a worst case weather week. Okay, more details can be found in Zoe's talk referenced there. And picking up on that, to add a bit more context, is a recent paper from Catherine Deeming, who recently successfully completed her PhD Viva, so now Dr. Deeming, so congratulations again, Catherine. And this is a really neat paper that Catherine led, again, with a lot of the STEAM team involved. And this is showing potential for co-location of mine shafts and potential energy resources. So the larger, I guess, hexagonal blocked areas are mine water blocks within the central belt or across the central belt of Scotland. The black dots represent different mine shafts, and the circles are, depending on which side we're looking at, if we look at the left-hand side, those green circles represent a substation, so a power substation within 1 kilometre of a mine shaft. And from that, if we take the screening criteria of mine shafts being over 50 metres deep, a volume of greater than 1,000 metres cubed, then there's about 288 mine shafts in the vicinity of a substation. So that's when you're considering things like curtailed wind and other potential power sources to convert into heat for storage. If we look at the right-hand side, a little bit more related to Alistair's talk this morning, but this is energy from waste rather than data centres. And also I've got some heat pump information on there as well from major heat pumps for district heating networks. But in this case, we're going to focus in on the kind of the bluey, purpley circles. In this case, this is the energy from waste locations. And if we look with the same screen criteria, we've got about 28 mine shafts involved with that. And to give a little bit more detail where we're at for Monktonhall, that is the circle that's just located over to the right-hand side of the map, just about halfway in between Edinburgh and Dalkeith, which are indicated on there. Excuse me. So the STEAM project consisted of these 5 work packages. I won't go into too much detail here, but I'm just going to try and summarize some findings from each of these work packages, a bit of a tall order, the remaining time in this talk. So it'll be a little bit of a whistle-stop tour. So from work package 1, a resource appraisal, just to give an idea of the location of the site. So we've got a geological map on the left-hand side here. You can see the plot of land, the location of Monktonhall number 1 and number 2 shafts. And the right-hand side, just want to really kind of emphasize here and show we've got the area of land there owned by local council we're working with, and then we've got the Mine Remediation Authority compound around the Monktonhall number 2 shaft indicated there. And two features I wanted to highlight here is we've got the Miller Hill Energy Centre. So this is a heat from waste plant, and it's located about 300 metres directly away from the mine shaft. So it's potentially ideally located to provide some energy storage and top up from that when heat is being produced, but not directly needing used. Another thing to point out is that in terms of field sites and study sites, etc., this is one of the most environmentally friendly ones to get to because we're within walking distance of Shawfair train station. So it's a nice, easy location to get to as well via public transport. So quick go over some mineshaft characteristics. Here's a schematic on the right hand side prepared by Steph Flood. You can see the mineshaft's about 921 metres total depth, backfilled to 280 metres below ground, and water level it varies a little bit, but it's about 20 metres below ground. Okay, so the total volume of the shaft in terms of mine water is about 10,800 metres cubed. So if we raise that by 15 degrees Celsius, there's potential to store 188 megawatts of heat. Okay, in terms of putting that in perspective, that's about 10% of the local annual demand. So performed a bunch of activities, including CCTV inspection. So got these and show some images from that and also to highlight some of the colleagues involved in the project. So we've got Hua Chang Wang and Indrani Mukherjee up there working with some of the guys from European Geophysical who performed the CCTV survey for us. And that's me doing something as well on the map, being busy with the yellow high vis. And just to point out here in the right-hand corner, we see image of CCTV about 75 meters depth. That's the bottom of the rising main. So that was the pump interface that was planned to take mine water from this shaft and then transport it to a treatment site. So you see the headworks on the top left image there. So that would have at one point been planned to go to a treatment site. So we looked at a bunch of stuff. Primarily Indrani was looking at projections and trying to assess the geochemical risks of increasing the heat within the shaft. So this is some freak modeling that she carried out. And just some kind of general take homes is that, in terms of we've got increasing temperature along the x-axis in all three of these plots. But pH remains circumneutral with heating, so there's limited significance of potential acid generation in terms of risk there. Sulfate in water decreases based on all of our kind of sample depths. So that's a good thing for potential concrete integrity and avoiding sulfate acid attack. There is some considerations for ochre formation increases with heat, especially up to 55 degrees Celsius, which is the kind of value we're looking at in terms of supplying a district heating network. So something to consider there for further work. And in work package 2, shaft stability. I'll try and rattle through these a little bit quicker. So this is work carried out by Shang Tong and Hua Chan. And essentially what they've done here is done a lot of modeling work to demonstrate that the structural stress distribution in the shaft lining is good, regardless of the temperature increase. And then moving on to work package 3 in terms of heat accountancy, this is work carried out by Ian in the audience and Jess. And they performed some computational fluid dynamic modeling to assess the potential of mine shaft, in this case Monktonhall, for heat storage. Okay, so there's the model set up on the left-hand side. Shaft is in the middle, and they modelled about, I believe it was 50 metres in terms of the surrounding lining and as well rock. And here's some of the results from Jesse's modelling here. So some of the key take-homes from this are that buoyant flow works in our favour. At the mixing zones, we've got down to 31 metres here, and you can see on the right-hand side that those convection currents are formed. But that mixing zone is relatively limited in terms of that circulation. But we still have a little bit of uncertainty in terms of heat transfer from what would be a planned closed-loop system in terms of supply of heat in this case. And we've also done it for the energy systems work package. There's a paper by Weneng, and there's been a more recent paper from Graham as well, Graham Flett, that I've got detailed at the end of this presentation. And they had a look at the levelized cost of heat sensitivity based on a number of factors, but essentially for low fuel costs, if we're looking at power, Mineshaft thermal energy storage had a minimal impact on levelized cost of heat, but had a much bigger impact in terms of lowering levelized cost of heat on the heat front. And for high fuel costs, which is what we're primarily looking at in the UK, then there's significant and competitive roles to play for levelized cost of heat in terms of Mineshaft thermal energy storage. And this is the work package 5, and also as well a little bit of a summary slide. So the plan from the outset for this project was to complete a heat injection experiment. Now we didn't quite get there, and the project ends in July, so we'll perform that during the lifetime of this project. But in terms of achievements done within the time frame, so we got the site access agreement completed. We completed the baseline characterization, done the experimental design. That was subcontracted to Town Rock, so thank you very much to them. And our Mine Remediation Authority heat access agreement, the discussions are ongoing there, and that's been a lot of effort on both sides going forward, but hopefully formed a really good and useful exercise for everyone involved as well. And now we're at the stage of seeking further funding to complete the heat injection experiment. And we've been working with some of the folks in the room and also the Mine Remediation Authority to identify opportunities for that. And we have submitted a couple of applications that will hopefully allow us, if they come off, to perform this heat injection experiment. So I just want to highlight finally, or second to finally, some of the publications that come out of the project so far. We've still got more to come. So we're kind of writing up results just now. We've got some recent publications in there. So if there's anything from these slides that I've not explained to the adequately, then please check out some of these papers. And finally, just want to highlight this journal opportunity. So Ian and myself are guest editors on a special issue of water on mine water utilization sustainable management, which just went live yesterday. So of all the brilliant talks that have been so far, it'd be great if you would consider submitting kind of follow-on papers to this journal. We've had a few comments already, which is fantastic, and thank you very much to people that have done that. You can go to the QR code or use that link, and if there's any further questions about this, you can ask either myself via email and Ian via email or over coffee if he's still around. Thank you very much.